Welcome to this video lecture which presents a number of hypothesis tests. We're going to begin with a test about the variance, the one sample variance test. If we want to test whether the population variance equals sigma squared, then of course we take a sample from that population, a random sample, we calculate the sample variance and see if the sample variance is consistent with the hypothesized population variance. The sample variance follows a chi-square distribution, so the statistic is chi-square, which is n-1 times s squared over sigma squared, and this test does assume a normal population. For an example here, we have the diameters of bagels are required to have a standard deviation of 2 millimeters or less. It's assumed that the bagels currently being produced conform to this requirement. Do these randomly sampled data assert otherwise at the 5% level? So here we have the diameters 97, 94, 96, 95, 99 and 93. Are those data consistent with the belief that the standard deviation is 2 millimeters? So we'll lay out the hypothesis test like this. If the standard deviation is 2, then the variance is 4. So the null hypothesis says the variance equals 4. Sigma squared equals 4. The alternative says sigma squared is greater than 4 because that's what would be a problem according to the statement of the problem. Anything less than 2 for the standard deviation is not a problem. So anything greater than 4 for the variance leads to rejection of the null hypothesis. N equals 6, the sample size. S, the standard deviation calculated from that sample, is 2.16. And so the chi-square value is 6 minus 1 times 2.16 squared over 4, which is 5.832. So as always, we leave that number there and then we go and take a look in the tables. So we go to the tables of the chi-square distribution and we enter the tables at row 5 for 5 degrees of freedom, and we look under the 5% heading, the 5% column, and the entry in the tables is 11.070. So we compare the 5.832 with the 11.070 and we see that the calculated value, 5.832, is not more extreme than the 11.070. It does not fall into the rejection region. And so we accept the null hypothesis that the sigma squared equals 4. These data do not prove that the variance is greater than 4, or in other words, that the standard deviation is greater than 2. We now look at a two-sample variance test. We want to see if the variance is the same in two populations, or if we can say that there's a difference. So the test statistic, F, the variance ratio, is the variance in sample 1 divided by the variance in sample 2, based on the samples. And of course, we always set up this test so that S1 squared is greater than S2 squared. So we calculate the variance from each of the samples, one sample from each population, and then we divide that larger variance estimate by the smaller variance estimate. The condition of using this is that we're dealing with normal populations. So we have two random samples of paint specimens. And the thickness measured in microns. We have a sample by brush and a sample by sprayer. And we're interested to know, is the variance different? Is the paint thickness more consistent with one method of application rather than the other? So we calculate the sample statistics. In sample 1, we have N1 equals 6, S1 equals 32.13. In the second sample, we have N2 equals 8 and S2 equals 9.47. So we take the bigger variance, 32.13 squared, and divide it by the smaller variance, 9.47 squared, and we get the ratio, the variance ratio is 11.51. That was taking the first sample variance divided by the second. So we have divided a variance based on 5 degrees of freedom by a variance based on 7 degrees of freedom. So since the degrees of freedom are 5 and 7, we go to the tables of the F distribution, which you can find on the last page of the textbook. And we go to 5 along the first row of the table, which is the numerator degrees of freedom, and 7 in the first column of the table. And where that row and that column meet, 5 in the first row, 7 in the first column, and we find that the entry there is 3.972. That's the critical value of F, the upper 5% value of an F distribution having 5 and 7 degrees of freedom. Our calculated value is 11.51, which is greater than this value. So it lies in the tail, it lies in the rejection region. And therefore we reject the null hypothesis. So the variances are not the same. Sprayed paint exhibits less variation in thickness than paint applied by brush. Here we have another hypothesis test, this time for a goodness of fit. Sometimes it's believed that a set of data belongs to a certain statistical distribution, and we can test whether that's the case. And this can be very useful because certain statistical distributions are based on certain assumptions about how the underlying process behaves. And if we can compare a set of data with the distribution that it's believed to be from, and especially if we find that it does not come from that distribution, this alerts us to the fact that there is something present in the process which we maybe hadn't been aware of. And so this can be very useful in pointing out issues that are present in a process. So the way we perform this test is that we compare the observed with the expected frequencies. The observed frequencies from the data that arises from the expected frequencies, which are the data that would arise from the process or would be expected to arise in the process if that distribution did apply to the data. The degrees of freedom is k minus j minus 1, where k is the number of categories and j is the number of estimated parameters estimated from the data. The condition for using this is that there's at least 5 categories and all the expected values should be at least 1. So we're going to look at a die that's rolled. So if a die is rolled 30 times and the outcomes are shown there, the question is it a fair die? A fair die should provide the numbers 1 to 6 with equal probability, 1/6 each time. So in 30 rolls, we would expect to get 5 of each of the outcomes. 5 times 1, 5 times 2. Now, of course, we don't get that every time. And so the question is the evidence here from the observed data, is it strong enough for us to say that this is not a fair die? Or is this consistent with the type of random variation that would be expected to arise in a process like this? So the null hypothesis states that the population has a uniform distribution with parameter k equal to 6. In 30 rows, the expected frequencies are 5, 5, 5, 5, 5, 5. The chi-square is 6 minus 5 squared over 5, and so on. We go through each of the observed minus the expected squared, divided by the expected. When we add all that together, we get 3.6 as the calculated value of the test statistic. So we leave that number there, and then we go look in the tables. We have 6 minus 0 minus 1, which is 5 degrees of freedom, because there are 6 categories in the data. We didn't estimate any parameters from the data, and we subtract 1. And so that gives 5 degrees of freedom. So we go to the tables of the chi-square distribution, enter the tables at row 5, because we have 5 degrees of freedom, and look under the 5% column. And we find that the critical value is 11.070. Our calculated value is a modest 3.6, which is in the acceptance region. So we accept the null hypothesis. There's no evidence in that data set that the die is not fair. So we accept the hypothesis of a fair die. You can read more about this in chapter 5 of the textbook.